Alright, hello everybody. Sorry I'm not here today, but here are the notes for the new material, and then once you have gotten these notes, you'll work in the packet. We're going to skip Chapter 6 and we're going to go to Chapter 7. So right now we're going to be talking about 7.1, and this starts a new unit. Not only a unit, sorry about that. Spelled that wrong. Not only a new unit, but a completely new topic. So we're done with functions and logs and all that stuff, and we're going to start our big trig part of pre-calc. So for some of you, this is going to be kind of like a clean slate. If you're not good at logs or some of the other stuff that we did, everything kind of starts over right now. So pretend like if you struggled, that you haven't. Everything's good, and if you've been doing well, hopefully you can keep doing well. This is going to be a little different than the stuff that we've been doing. So anyway, let's start with the actual definition for a radian measure. Let's say we have a circle, and in the center we have two radii drawn, and then we have an angle here called theta. The definition for a radian, which is the measure of this central angle, is to simply take the arc length, which we're going to call S, and then divide that by the radius. Okay? So this is the definition for a radian angle. Okay, on your calculator you have two different kinds of angles. If you go there in the mode, you'll see that there's degrees and there's radians. So now you're starting to learn what radians are and how they're tied to degrees. Okay, so this is the formula to calculate a radian central angle given a circle. So for example, if we have a circle and it looks something like this. Let's say the arc length is 3 centimeters and the radius is 4 centimeters, and I ask you to calculate that angle. We can certainly find it in degrees, but in radians, all we would do is take the arc length, which is 3 centimeters, divided by the radius, which is 4 centimeters, and we get that this angle is 3/4 radians. Okay, you don't have to write radians for the angles. In fact, a radian is considered the unitless angle. Okay, if there's no degree symbol here, then you're always going to assume that we're talking about radians. Okay, so that's pretty straightforward to see how you find the radian angle for a central angle of a circle. Okay, so now the next thing we're going to talk about is the connection to degrees. And we'll actually start with this example again. Let's say we have a circle and we're interested in finding this entire angle. So not just like a little part of a circle, but all the way around the circle. Okay, well, we know that a circle has 360 degrees all the way around. Okay, and now what we want to do is maybe figure out, so this is degrees over here, and now we want to figure out what this is in radians. Okay, well, in radians, we know that theta is equal to S over R. Okay, so up here it was pretty easy. The arc length that corresponded to this angle was 3 centimeters. Well, if I'm interested in the entire angle that goes around the circle, instead of the arc length, we're actually talking about the circumference of the circle. Okay, and now the formula says to divide by R, So we'll also divide by r here. And now we actually find that in 360 degrees, if I put it in radian form, it's equal to 2 pi radians. Okay? So this is your first link or your connection to radians. And you're going to memorize these, by the way. 360 degrees is the same as 2 pi radians. Okay? And if you cut this in half, you get the conversion that 180 degrees is equal to pi radians. This is probably the most important one for you to know right now, because we'll utilize this here in a little bit. But you can get pretty much any connection that you need. For example, cut it in half again, you get that 90 degrees is pi over 2. So if you just divide this by 2, you get 90. Divide pi by 2, you get pi over 2. One more time, we get 45 degrees is pi over 4. Okay, and these are some pretty common angles that we're going to deal with later. Okay. Now, one of the skills that you need to know how to do is to actually convert back and forth from degrees to radians and radians to degrees. And actually, it's all based off of this link right here, that 180 degrees equals pi. Okay, so we're going to use 180 degrees equals pi, and here are some examples. Okay, so for example, if we want to convert 63 degrees into radians, we'd simply do some unit analysis. Start with 63 degrees, and now if we don't want degrees anymore, we're going to put the degree unit on the bottom. And our link is that there's 180 degrees in pi radians. So now if you go ahead and multiply this out, the degrees will actually cancel out. Degrees divided by degrees gives us nothing. In other words, we're going to end up with radians. And we get 63 times pi divided by 180, which reduces to 7 pi over 20. Okay, so 63 degrees is the exact same thing as 7 pi over 20 radians. Okay? Another example going the other direction. Let's say we wanted to convert 17 pi over 2, which is currently in radians since there's no degree symbol here. So let's say we wanted to convert that into degrees. So we do pretty much the same thing. Take 17 pi over 2, and our conversion is that there's 180 degrees in pi radians. Now we just switch the location of the degree symbol. Since I want to finish with degrees, we put pi radians in the denominator, and now we multiply. And if you multiply 17 times 180 divided by 2, you get 1530 degrees, and notice the pi's will cancel out. Okay? One more. Let's say we want to convert 2 radians into degrees. Okay? So, same idea. I just want to make a point here that a radian angle does not necessarily have pi attached to it. So some of the examples we've seen all had pi. We don't need pi, and here's an example of one. So let's say we wanted to have 2 radians converted into degrees. We do the same thing. 180 degrees in 2 pi radians. 2's cancel, and now we get 180 degrees over pi, which is approximately, let's see, $57.3 or so. Okay, so this would be the exact value. 180 divided by pi is the exact. 57.3 is the approximate. Okay? Alright. Now, let's talk about some other things. So we've talked about radian angles, how to convert from radians to degrees. Okay? Now what we'll talk about is sector area. Okay, so let's change colors here. So again, we start with a circle. Let's say we have a central angle theta. This piece of pie, so to speak, that's shaded in here, this is called a sector. Okay, and if we want to figure out the area of this sector, we can kind of think about this as being a percentage of a circle. Okay, so one way to think about it is to do this. In a circle, there's 2 pi radians, and if I take theta, so if I take this angle, which is a certain percentage of 360, or of the 2 pi radians, divide it by 2 pi, this is kind of like the percent of the circle. And now if we want area, let's multiply that by pi r squared. Okay, so now we get a formula that looks something like this. Pi's cancel, we get 1/2, and if I rearrange the terms, 1/2 r squared theta. So this is how you find the sector area, keeping in mind that this is a radian angle. Okay, so this formula is a nice little shortcut to find sector area if it's in radians. So for example, let's say we have a circle, and let's say that this is 120 degree, that's for the central angle, and let's say this radius is 3 meters, and we want to find the sector area. Okay, so sector area is simply 1/2 r squared theta. So we're going to do 1/2 radius squared, so 3 meters squared, and then theta, theta is 120 degrees. This needs to be in radians, so we actually have to convert. So let's convert 120 into radians. So 120, if I want to convert into radians, degrees needs to go on the bottom. So 180, pi on top. 120 pi divided by 180, that's going to be 2 pi over 3 after you reduce the fraction. Okay, so we're going to put 2 pi over 3 in here for theta. So once again, 1/2 radius squared. This theta always needs to be in radians. If it's not, then you need to convert it. And after you simplify, you're going to get, let's see, 2's cancel, 3's cancel, or no, let's see, 1/2, 9, 2 pi over 3, so we're going to get 3 pi, and we are meters squared for the units. Okay? Pretty straightforward calculation. Now obviously you're going to have to know how to work backwards too. So if I give you an area and I give you a radius, you should be able to go backwards and find the angle, or maybe find the radius if I give you the angle. Okay? Let's see. Drawing angles. Okay, so let's say this is a little, well, it's a little different. We're going to go on the XY plane now. Okay, so this might be jumping ahead a little bit, but it will help out for later. Okay? When we draw angles on the XY plane, we're always going to start right here on the positive x-axis. Okay? And then we're going to rotate counterclockwise. So, whenever you see an angle, like let's say, for example, 220 degrees, okay, you're going to start right here, you're going to rotate counterclockwise, and you're just going to estimate. For instance, right here is 180 because that completes the line. So I'm going to go about 40 degrees more, and then we draw what we call the terminal part of the angle, Okay, so this angle here is 220 degrees. Okay? Now, something that's going to be very useful for us later on, let's say we have an angle here with respect to the nearest x-axis. Okay, so wherever the terminal part of the angle is, find the x-axis, whether it's the negative or positive side, whichever is closest. You make an angle there. That's the reference angle. Okay, we're going to use those a lot. So this is called a reference angle. And if we found it here, pretty easy. If this is 220, think about how many degrees it took to get here to the x-axis. So this was 180. We add 40 more degrees to get to 220. So the reference angle there would be 40 degrees. Okay, so that's how you would draw angles. You can certainly do this also with radians. So for example, if we wanted to sketch 3 pi over 4 in standard position, okay, if you're not sure where this is, you can certainly convert it to degrees. But if you see this 3/4 there, that means that you're going 3/4 of the way to pi, which we know pi is 180. Okay, so if you converted this, you'd get 135 degrees. You don't need to, but since you're going 3/4 of the way to pi, or 180, this would be a decent sketch. Okay, so 3 pi over 4 looks something like this. And now the reference angle, so in this case, if you can't find it, you can do pi minus 3 pi over 4 if you're not sure what it is, and you get pi over 4. And the reason we're doing pi minus 3 pi over 4 is because all the way to the x-axis is 180, or pi now, and then we're going to subtract 3 pi over 4 to figure out this difference, which is the same as pi over 4. Okay, so that's kind of how you sketch angles. Let's see. I think there's only one more topic and a few more examples. Angular speed or velocity. Okay. A good way to think about angular speed is angle. How much angle, let's say it that way, how much angle per second or per whatever unit time. So for example, if we have a wheel or something circular and it rotates a certain angle, then what we can do is find how quickly it's rotated. So the unit for angular speed or angular velocity is what looks like a W. We call it omega. Okay? And to figure out how much angle per unit of time, you simply take the angle in radians and divide it by time. Okay, so again, this is another formula now that's in radians. And now we can tie this together to linear speed. So for instance, okay, here's a good distinction between angular and linear. So imagine, let's draw another circle. Imagine we have a merry-go-round, okay? Or one of those playground spinny thingies. Let's see, what am I talking about here? Maybe if I draw it like this. You guys know what I'm talking about? Hopefully you do. You know, and this thing spins around and you got someone standing here on the end, spinning, going woohoo! Because they're having a lot of fun, right? They're on the outside. Now, if you picture a merry-go-round, or this particular example, someone that's standing here on the edge versus someone that's standing So let's say this is the radial line versus someone that's standing right here in the center. Okay. In the same amount of time, both this person, this blue person, and this red person, they would have rotated the same angle. Okay? However, the person on the outside has a much further distance to travel than the person that's right here on the inside. Okay, so hopefully that kind of makes sense and helps you distinguish or tell the difference between angular speed and linear speed. Okay, so angular speed tells you how many degrees or how many radians have been rotated in a unit of time. Now linear speed, here's how we can find it. We know that linear speed is v equals d over t. Okay? And now, one way to link the two is to think, alright, well, if I want linear speed for this person on the outside, this distance is actually going to be an arc length that corresponds to this bigger circle on the outside. Or if I'm interested in this person that's on the inside, it's going to be a smaller arc length. Regardless, this d is really s for arc length over t. S is the same as r times theta. So I don't know if we made that clear or not, but here's my little clipboard. We know that theta is equal to s over r. Okay, so if I just multiply this equation by r on both sides, we get that s equals r times theta. So I'm just substituting for s r times theta. Okay, and now I'm dividing that by time. So now we get, if we simplify this a little bit, v equals r, and now theta divided by time is actually angular speed. Okay? So here are the two formulas for speeds. Angular speed is just the angle divided by time, and then linear speed we call v, and that's just the radius times the angular speed. Okay? So here's an example. Let's say we have a gear rotating at 100 RPM, which means revolutions per minute. Okay? And we want to find what the angular speed is, and let's say for part B, the linear speed. Okay, and let's say that here's our gear, and this particular gear has a 4 centimeter radius. Okay, so we want to figure out the angular speed of this gear, and we want to figure out the linear speed of whatever is 4 centimeters away from the center of the gear. Okay, so angular speed. So for part A, angular speed is simply theta over time. And all this means is how many degrees, but we're going to do it in radians. How many radians are covered in a unit of time? Well, if I know that 100 revolutions per minute is how quickly this is spinning, I know that in 1 minute, that's my time unit, I've gone around the circle 100 times. Now, if we think back to earlier, if I rotate 1 time around the circle, that's the same as 360 degrees, but let's stay with radians. If I rotate 1 time around the circle, that's 2 pi radians. Okay? So 1 revolution is the same as 2 pi. If I'm doing 100 revolutions, well, then I've really done 200 pi radians in 1 minute. Okay, so that's actually your angular speed. Done. 200 pi radians per minute. That's the angular speed. Now for part B, the linear speed, we use the formula V equals R times omega, radius times angular speed. The radius they gave us was 4 centimeters. Angular speed was 200 pi radians per minute. And again, we don't need to write the radians, but if it helps, you can do that. And if you multiply this out, you get 800 pi centimeters per minute. Again, we don't need the radians, those are unitless, but this is the linear speed of something that is rotating at 200 pi radians per minute. Okay, so these are the notes for 7.1. I know there's a lot of info in here and this is kind of new, so I'm going to recap for you the formulas that we've covered in this section and the ones that you need to memorize. Theta, the radian angle definition, is arc length divided by radius. If I multiply this equation by radius on both sides, we get that arc length is the same as radius times the radian angle. Okay. In addition, we also talked about sector area. Sector area was 1/2 r squared theta. So there's that. And again, this needs to be a radian angle. If it's in degrees, you have to convert it. And then we'll also write down the two that we just finished with. Angular speed is simply theta over time. Again, this needs to be in radians. And linear speed, V equals R times omega. So this is linear speed. Okay, so these are the formulas we've talked about. A lot of good stuff in this section that's going to help with all the trig things that we're going to do in this class. All right, hopefully I'll be back tomorrow. I'll see you guys. Homework will be day 1 from the book. You can look on Edmodo in the Chapter 7 folder, which I will put up. All right, farewell.